Okay, so yesterday we wrapped up with the superposition principle, which you should already have written down, which said that if you have several solutions to the
Norma Rothers, dial 7011. Norma, 7011.
That if you have several solutions to the homogeneous equation, then if you combine them linearly with constants, then that bigger solution will also be a solution to the original differential equation. So we're going to prove it because it's actually not that hard. So for simplicity, let's look at the case, again, where n equals 2. So that means we're going to have two solutions, y1 of x and y2 of x, be solutions to, or of, the second order equation, a2x y double prime plus a1 of x y prime plus a sub 0 of x times y is 0. Okay, and we're going to also let y equal, just like we said, c1 y1 of x plus c2 y2 of x. Okay, so then if I go ahead and take, after we do the superposition principle and get this new solution, the proof basically is plugging it in and making sure that it works, which isn't very hard. So if we go ahead and plug it in, the differential equation becomes, we're going to have a2 of x, and now here we want to do y double prime, so we're going to look at y, find the second order derivative of this function, which isn't hard because these are just constants, and we can just leave these as y1 double prime and y2 double prime. So it'll be c1 y1 double prime of x plus c2 y2 double prime of x. And I'm going to run out of space, but I'll just continue it here, plus a1 of x, and then what will we have here? Now it's y prime, so that's c1 y1 prime plus c2 y2 prime plus a naught of x times our original y, so we're just going to plug it in. c1 y1 plus c2 y2. And we want to verify that we get 0 here. So what we could do is maybe group out all the constants. So all three of these terms have a C1. And then if I factor out a C1, I'm left with what? A2 of x, y1 double prime, plus, here if I take out C1 from the C1 term, I get A1 of x times Y1 prime. And if I take out the C1 term from the last group here, you get A naught Y1. And now if I do the same with C2, so now take out all the C2s from the C2 terms, you're going to get exactly the same factor. Oh, not exactly the same, sorry. The only difference is what? Instead of Y1, it's Y2. Okay. Now, what does this equal? What does this equal? It equals this function, right? Just different y values, but no big deal. Y1, Y2, but what does that equal? 0. So this becomes C1 times 0 plus C2 times 0, which equals 0, which verifies that y equals C1 Y1 of x plus C2 Y2 of x is a solution. Okay. Pretty straightforward proof. This might be a good one for an exam. Questions on it? Yes?
Why did we initially set it equal to 0?
Well, because we're verifying that it's a solution to star 1. Remember star 1 from yesterday? Which was right here. So basically what we're doing is, since we've already dealt with linear first order, we said let's go just to order number 2. So we're still making it a homogeneous equation equal to 0. So that's why we started with this assumption here. This assumption up here. So that we let the two solutions at hand be solutions to the second order linear differential equation that equals 0. Does that make sense? So then, once you have that, all it is just like it was in unit 0, right? You take the derivative of y, take the second derivative of y, plug it into the differential equation, and you just verify that it all equals 0. Okay? Anything else? Okay. Yes? So the question is, where does this 0 come from here in this one? Okay. So all I'm doing is replacing this entire parentheses. You see the pattern here? A2, y double prime, A1, y prime, A naught, y naught, right? Or y. That's this right up here. So the fact that y1 is a solution to this means that if I were to plug in y1 in here, I should get 0. Does that make sense? Which is exactly what this demonstrates. It means y1 was plugged in, but I already know that equals 0. y2 has been plugged in here, and I know that equals 0. Make sense? Okay.
So how do we determine that C1 and C2?
Well, we don't need to determine it. That's like,
So anything.
yeah, I mean, the whole thing's going to be 0 anyway. You're thinking more along the lines of if we actually have a differential equation that we're solving with some initial values, then we can determine it. But this is just demonstrating that this works. So if the question is, well, how do we go back and find C1 and C2, right? You'd be given some initial values like y of 0 is whatever, and then y prime of 0 is some other number. And then you can plug them in, get a system, and then you get it there. But for the proof, you don't need to find the constants. You just need to make sure that they all add up to 0. Okay? All right. Everyone got this down? Okay, so a couple of things, some remarks. One, a constant multiple of y equals C1 y1 of x of a solution y1 is also a solution. And a homogeneous linear differential equation always possesses the trivial solution, what? Y equals 0. Okay? Obviously, if y is equal to 0, then all the derivatives are 0, y is 0. Of course, it's going to add up to 0. Okay? So those are two things that you should know going in. Okay. So again, we're laying down the framework where all these solutions come from, why these things work. We're almost to the point where we can start solving them and constructing these on our own, but for now, let's suppose that y1 equals e to the x, y2 equals e to the 2x, and y3 equals e to the 3x. And let's suppose that all these satisfy the differential equation, third order derivative minus 6 times the second order derivative plus 11 times first order minus 6 times y equal to 0. Now, you guys already know how to verify, so the point of this section is not so much plug all three of these in and convince yourselves that these work. We already know how to do that. What we want to make a note of here is that now that we've proved the superposition principle, by superposition, we can construct a more powerful solution, so to speak. What would that be? Well, I'm sure Adrian can help us out. No? Superposition principle. What did it say? Nope, not even that. All we're doing is combining all three solutions with constants. Yep. Yep, that's it. Is also a solution. Okay. That's all it says. If you have three solutions that you know about, you can combine them with C1, C2, C3, add them all up, and that will build another solution for the set, or for the differential equation. Well, you don't have to find them, no. We will eventually, yes. Yes. So if it's an IVP, you might have three initial conditions given, right? Y of 0 equals whatever, y prime is equal to whatever, and y double prime, and then you can create a system. Okay? Oftentimes, though, we won't even find it. It'll just be solve the diff EQ, not necessarily an IVP, and this is what our solution is going to look like. Ah, that's a great question. So why is this considered better? Okay, the point is, for these differential equations, there's a lot of times like little oddball solutions that work, like this one works all by its own, this one works all by its own. But remember when we first started talking about diff EQ, we said that a third order equation, we should expect to have how many parameters? 3, right? Fourth order, 4. N order would have n parameters. So this, even though it's a solution, it's not what we call the general solution. Does that make sense? This by itself, not a general solution because it doesn't have any parameters involved. Same thing here. But now the superposition principle allows us to combine these in this manner with parameters C1, C2, C3. And now the point of this is, will this be, the general solution to the equation? And then that's what we're leading to. Okay? Now, before we get there, though, let's just talk about this real quick. When are solutions linearly independent? What have we talked about as far as linear independent? Very good. Wronskian. So if we have y1, y2, y3, and we want to verify whether or not these are linearly independent, we can compute the Wronskian. Okay, so we use the Wronskian, and we want to make sure that the Wronskian of those three is not equal 0 for some x and I. Okay? And now this is what we were just talking about, Eric. So here's the official terminology now. A set of linearly independent solutions y1, y2, and so on, for an nth order differential equation, specifically homogeneous linear. That's what we're talking about right now. On an interval, I, is called a fundamental set of solutions. And now the general solution is found as follows. If y1, y2, y sub n form a fundamental set of solutions of the homogeneous linear differential equation, which is star 1, then y equals c1 y1 plus c2 y2 and so on is the general solution. And that's what we're in search of. Okay, so we have all these little building blocks. Okay, we have, first we need to know when we have a unique solution, which we've already assumed that for this case, homogeneous linear differential equations, all the coefficients are going to work out so that they're continuous. The lead coefficients never equal to 0. So we know that this is unique already, which is nice. So that's the first thing. The second thing is, in order to have a general solution set, each individual solution needs to be linearly independent. Okay? And that's what we talked about. That's why we talked about the Wronskian, because we can use that to verify whether it is or not. Okay? So here's an example. Try this on your own real quick. Let's say y double prime minus 9y equals 0 possesses y1 equals e to the 3x and y2 equals e to the minus 3x as solutions. What is the general solution? And why? Okay, so take a minute or two, work on it, we'll go over it, and then we'll finish up the lecture.